In this lecture, we will talk about inversions of lines with respect to a given circle. Inversions with respect to a circle are also referred to as reflections across the circle. On the diagram shown below, we are given a circle with center 0 and radius r. Included in the diagram is line L that we will invert with respect to the circle C sub 1. Let P be any point on line L. P' is the point of inversion of P with respect to the circle. We say that the points P and P' are inverses with respect to the circle if the product of the lengths of the segments OP and OP' is equal to the square of the radius. We also have the added requirement that O, P' and P have to be collinear, with O being outside the segment P', P. Our objective is to show that as P travels along line L, P' will trace a circle. We will make one allowance for what it means to be a point on line L. Lines don't have endpoints. We will pretend that there are points at infinity or on the horizon so that effectively L has endpoints at infinity. As P tends to either point at infinity, observe that P' tends to the center of the circle C sub 1. We then have the symmetric relationship that the inverse of the point at infinity is the center O. Allowing for the point at infinity, we will show that the locus of the point P' is a circle. Here is our strategy for the proof. Through the center O, we construct the perpendicular to line L. Let this perpendicular and line L intersect at the point Q. Let Q' be the inverse of Q with respect to C sub 1. Now, for the moment, we will assume that P and Q are distinct points. One can easily adjust the proof to include the case when P and Q happen to be the same point. And so for the case when P and Q are distinct points, we will show that the angle OP'Q' is a right angle. This is central to the proof that the locus of P' is a circle. And so the 3 points OP'Q' will have to be non-collinear, and 3 non-collinear points determine a unique circle. We also have a right triangle that is inscribed in a circle. If a right triangle is inscribed in a circle, then its hypotenuse is the same as a diameter of the circle. Note that this hypotenuse depends only on O and Q'. Q' depends only on Q. Q is independent of P. So the diameter OQ' stays the same no matter where P is on line L. And so the locus of P' must be the circle whose diameter is OQ'. For the case when P and Q happen to be the same point, Q' will be the same as P'. Q' being the endpoint of a diameter means that P' will also be on the circle. We proceed with the proof that angle OP'Q' is a right angle. Let theta be the angle P'OQ'. To show that angle OP'Q' is a right angle, we will examine a pair of triangles and show that they are similar. The first triangle is triangle OP'Q'. The second triangle is triangle OQP. In order to show that the two triangles are similar, we will show that corresponding sides between the two triangles are proportional. The first pair of corresponding sides between the two triangles is made up of segment OP from the big triangle and segment OQ' from the small triangle. Then we have the pair that is made up of segment OQ from the big triangle and segment OP' from the small triangle. The third and final pair of corresponding sides is made up of segment PQ from the big triangle and segment P'Q' from the small triangle. Recalling what it means for points to be inverse points with respect to a circle, P and P' are inverses with respect to C sub 1 if the product of OP and OP' is equal to the square of the radius. Q and Q prime are also inverses with respect to C sub 1. And so the product of OQ and OQ prime is also equal to the square of R. We divide this equation by the product of OP prime and OQ prime. We get OP divided by OQ prime equals OQ divided by OP prime. This is our constant of proportionality, and we will call it K. And so we have that OP is equal to K times OQ prime and OQ is equal to K times OP prime. To proceed with the proof, we apply the law of cosines on the big triangle. Using the angle theta and the opposite side PQ, we have the square of PQ equals the square of OP plus the square of OQ minus twice the product of OP and OQ times cosine theta. We replace OP by K times OQ prime and OQ by K times OP prime. Consequently, the square of PQ is equal to K squared times the square of OQ prime plus K squared times the square of OP prime minus 2K times OQ prime times K times OP prime times cosine theta. We factor out K squared and observe that the quantity inside the parentheses is the law of cosines applied to the small triangle. And on the small triangle, the side that is opposite theta is the side P prime Q prime. And so what we have inside the parentheses is the square of P prime Q prime. Therefore, the square of PQ is equal to K squared times the square of P prime Q prime. Taking non-negative square roots of this equation and dividing by P prime Q prime, we get PQ divided by P prime Q prime equals K. So we have three pairs of corresponding sides between the two triangles, and these corresponding sides are proportional, and so the two triangles must be similar. We know that corresponding angles between similar triangles are congruent. Angle OP prime Q prime corresponds to angle OQP, which is a right angle. Therefore, angle OP prime Q prime must be a right angle. Therefore, the hypotenuse OQ prime is the fixed diameter of the circle, which is the locus of the points P prime.